discussion on continuity is about how functions act and if there's some bad places in a function or not, some places that look bad. So the idea of continuity intuitively we understand. So let me just start out with something very simple, that if we had the graph of a function, of course here's the x-axis and here's the y-axis, and suppose we see the graph of this function, and maybe it looks something like this. So this is the graph of f. We could look at that line and say, oh, that's a continuous line, meaning there's not any breaks in it, there's nothing strange going on, and so just intuitively we might say the function, or f of x, is continuous. Now, on the other hand, if we have a function g and we looked at its graph, and maybe its graph looks something like this. It goes along and then all of a sudden it hits a spot and it ends at that spot, and then it jumps up above and it starts someplace else. Now, suppose that's the graph of the function g. Well, it's clear that that graph is broken, or we can't draw that line in a continuous fashion. So we could easily say, and it makes sense, that g of x is not continuous. There's a broken place or a bad place in the graph. Is not continuous. And when it's not continuous, we say it's discontinuous. If specifically this break in the graph happened at the x value of a, we could further say that g of x is discontinuous at x equal a. If we look at the graph anywhere away from a, then it's a continuous line. So only bad place is when x is equal to a. Well, in mathematics, we need to be a little more precise. And so let me kind of give us three graphs of situations that we want to prevent. And when I say we want to prevent, it's a lot easier to work with graphs that are nice, or functions that are nice. That is, functions whose graphs don't have any breaks in them or don't have any holes in them. Those are easier functions to work with, and those are our continuous functions. So let's look at three scenarios, which will be three different graphs. We don't know the formulas for these graphs, but here might be the first situation. And I'm going to look at the graph of f. Suppose this is where the x value of a is. And we see this graph, and it comes along, and right here where a is, there's a hole in the graph. We've seen this type of situation already. Well, and this is the graph of f. The problem with this graph, as we see it, the function's not even defined, and I apologize. I think our book actually uses a value c here. Hold on just a moment. Let me pause. Okay, to be consistent with our book, and that's what I was checking. Our book calls this value of x some c value instead of the a value. So c represents some number that's an x value. So the hole in this graph appears when x is c. And that hole being there means that it means what we see is f of x is not defined, is not defined at c. In other words, f of c does not exist. Okay? That's what that graph is telling us, that there's no y value when x is c, or f of c is not defined. Another way to say that. Another situation that's a bad situation is when the graph doesn't necessarily just have a hole in it, but there's a break in the graph. So once again, let's suppose that our x value that's c is about right here. And we see a graph, in this case, kind of like what we had above here. It comes along and stops at c, and then it jumps up and starts again. Okay, so maybe this is the graph of f of x. Now, in this case, we see that f of c is defined because there's a y value, there is a point that goes along with the x value c. So notice f of c exists, but there's another problem here. That's okay, but the problem is that the limit of f of x as x approaches c does not exist. And we've seen that idea before because the graph is completely broken. Okay? And a third situation that could occur would be related maybe to the first situation. And that is we have a graph, okay, that comes along. Let's say this is where C is again. Comes along, and of course there's a hole in the graph right here. But unlike the situation before, this graph is actually defined as C. So it's kind of like we take that hole and put the point that should be in that hole someplace else. Now let's suppose this is up here at a value L. And let's call this, actually this y value is f of c, isn't it? See, that's the y value when we put c into the function f. Remember, this is the function f. So in this case, we see once again that f of c exists. It has a place on the graph. It's not in the right place. And we see that the limit of f of x as x approaches c exists and is in fact equal to L. See, the limit we would get as x approaches c, we'd be getting close to the y value of L above. So the limit exists. Okay, not only does it exist, we know that it is equal to L. But the problem we have here is that hole ought to be filled in. The limit is equal to L, but that's not the same as f of c. And so the broken part here, if you would be, if we could say, is the limit of f of x as x approaches c is not the same as the way the function is defined at c. It's not equal to f of c. So all three of these situations are bad. Remember, the very first one is bad because f of c does not exist. So the very first one is bad, and here we go, is because f of c does not exist. The second one is bad because the limit of f of x as x approaches c does not exist. And the third one is bad is because the limit is not equal to the same as the function at that position. So here's what I was headed for. We say a function f is continuous at the number c provided the following three conditions are met. And the very first condition is that f of c must be defined or exist. F of c must exist. That is, be defined. So you see in the very first example up here, that function is not continuous at c because f of c does not exist. The second condition that is required for a function to be continuous at c is that the limit of f of x as x approaches c must exist. Okay. And in the second example up above, we see that, as we said, that is not continuous because the second condition fails. The limit of the function does not exist as we approach C. And the third condition that must be true prevents the third situation we see in the third graph. And that is, not only does the limit have to exist, the limit of f of x as x approaches C must be equal to f of C. In other words, there shouldn't be a hole in that position. Even if f of C exists, it's got to exist to be the right thing. Anyway, these three conditions must be true for a function to be continuous at C. And in this case, that prevents the three situations that we see above. None of the three above are continuous at C. The first one breaks rule 1, the second one breaks rule 2, the third one breaks rule 3. Now, if a function is not continuous at C, if any one of those conditions fails, if a function f is not continuous at C, that means it breaks one of these three rules. Then we say f is discontinuous at C. So one more thing I want to say before we leave this page is, if you look at this third condition, remember when we were calculating limits by the substitution method? Well, that's really what this is saying, that the limit of f of x as x approaches C would be the number we get if we replace x with C, if we substitute a C into the formula. And so this actually says that calculating the limit is easy. It can be done by substitution, provided we have a continuous function. So the substitution, that's what this really is saying. The substitution method of calculating a limit works when we have a continuous function. And that's really where that third situation comes from. So let's look at our first example, or our first problem. And as you can see here, the problem is stated as, is the function f of x equal 1 over x minus 2 squared continuous at x equal 2? And remember, there's three conditions we have to consider to decide whether it's continuous at x equal 2. And so the first condition is, we're asking the question, does f of 2 exist? Okay, that's the first question. And we can see, of course, here that if we substitute a 2 in, for x, we'll get a 0 in the denominator, and so the answer is no. And for that reason, then f is not continuous at x equal 2. So we've answered the question very quickly, but just noticing that f of 2 does not exist. Now let's carry this a step further, though, because I would like you to see that there's some other issues here that are worth discussing. And I don't know if you remember what this graph looks like, but really this is a transformation of the graph 1 over x squared. And since we're subtracting a 2 from x, that causes a horizontal shift to the right 2 units. So let me show you what this graph looks like. There's where x is equal to 2. And at that point, we actually have a vertical asymptote. Remember studying that in college algebra. And in this case, all of the y values will be positive because we're squaring values. So here on the left side of this asymptote, we'll have a branch that looks something like this. And on the right side of this asymptote, we'll have a similar branch that looks like this. Now, condition 1 failed because the function's not defined at x equals 2. But let's consider condition 2. Does the limit of f of x as x approach 2 exist? And that's really the question. And of course, as x approaches 2, from either the left or from the right, what's happening for the y values? They're going up, up, up. No matter which side we're coming from, they're going up, 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 aren't they? And so we remember when we were talking about limits, when we get unboundedly large or unboundedly small, that is, it keeps going up forever or down forever, then sometimes we say the limit is infinity. That is, we might in this case say the limit of f of x as x approaches 2 is infinity. But remember, for purposes like this, we said that really means the limit does not exist because we're not getting close to a number. So does not exist, we might say here as well. Okay, infinity is not a number, so f of x is not getting close to a number. So condition 2 also fails. And likewise, condition 3 fails because condition 3 says not only does the limit exist, it has to be equal to f of 2. But the limit doesn't even exist, so there's no way condition 3 can be true also. So this is, in all 3 cases it fails, but it's not continuous because it failed the very first one. We didn't even have to go past that. And we can say in this case that f is discontinuous. Whoops. My hand's not wanting to write, or my pen's not wanting to write what my hand wants to. F is discontinuous at x equal 2. Now here's a little bit different twist though. If we look at all x values except 2, see, if we're looking at this function and we're not looking at 2, then we're maybe just on this part of the graph. And that part of the graph can be drawn without ever lifting our pen or pencil. So as long as we're not looking at 2 or we're on the right side of 2, that's a continuous line. And if we're on the left side of 2, the graph is a continuous line. And so in this specific case, we might say that f is continuous on its domain. That is, for every value of x that this function is defined for, it's continuous. It wasn't defined for x equal 2. It's not continuous there, but for all other values it was or is. Okay, let's look at an additional problem. And this problem is stated in this fashion. Find any discontinuities for or of f of x is equal to x squared minus 5x plus 6 divided by x minus 3. Now, we discussed just a moment ago that a function is discontinuous at values where the function is not defined. And we can look at the denominator here and decide the function is not defined. That is, f of 3, f of 3 does not exist. So that implies that x equal 3 is a discontinuity. Okay. Now, I would have a reasonable question. If I were you, we can recognize that, but there are some other discontinuities. And how are we going to make that decision? Well, it would be a lot easier if we had a graph of this function. And of course, that can be difficult in itself. But let's try to figure out what this graph looks like, and then we'll be able to tell if it has any other discontinuities, I think. So what does the graph look like? Well, before we just start plotting points, we've seen this idea before. What if we look at this function and notice in the numerator, I think, we have something that's factorable. So if we factor that numerator, I think it will factor as x minus 3 times x minus 2. And the denominator is x minus 3. Now, I'm going to come back up here and change this. We recognize that in this function, x cannot be equal to 3. And so we also know here x cannot be equal to 3. Now, if we cancel, we're changing the function a bit. If we cancel these x minus 3s, but that's all right if we remember that x couldn't be 3 to begin with. Because if x is 3, this we're not defined, but x minus 3 over x minus 3 for all other x values is just 1. So this simplifies simply to x minus 2, as long as we remember that x could not be equal to 3 in the very beginning. Now, when we look at that, we see that if we were to graph that, it's just going to be an ordinary line. Except it's an ordinary line where we can't use 3 for an x value. So it's an ordinary line with a hole in it. We've seen this idea before. So let's think about plotting some points, just to make this easy. And so we might choose x of 0, and our y would be negative 2. And we might choose x of 1, and of course our y is negative 1. And what am I doing? I'm putting those x values into this function, aren't I? And I might choose x to be 2, and of course if I did, we would get a y of 0. Now I can't choose x to be 3 because the function is not defined at 3. So I really can't use that. But suppose I did, then I'd get a y of 1. And so that was really telling me where the hole in the graph is. Since I can't use 3, I won't get 1 for y. Okay? Now anyway, let's skip over that 3 and try a 4 for x. And if we choose 4 for x, of course, we get a 2 for y. Now, when we graph this function, let's go over here and make a graph of it. Okay, so here's 1, here's 2, here's 3, here's 4, here's 5. Suppose here's 1, here's 2, here's 3, here's 4, and so on. So when we plot, and here's negative 1, and here's negative 2. So when we plot 0, negative 2, we have this point. And when we plot 1, negative 1, we have this point. And we plot 2, 0, we have this point. And we can't plot 3, 1 because that's not really on the graph, but that's where our hole is, isn't it? And when we plot 4, 2, we would have this point. And so when we draw our graph, we're going to see that it looks like this, of course, with that hole. Now that we see the graph, we can see that the only suspect place is where x is equal to 3. That's the only place that looks bad on the whole line, and so we recognize then that our function will be continuous everywhere else. So our conclusion is x equal 3 is the only discontinuity. Okay, and so we've answered the question that well, the original question is find any discontinuities, and we found that there is only one. In our next problem, we're asked to find the discontinuities of the piecewise defined function we see here. F of x is equal to 2x minus 1 if x is less than 2, f of x is equal to 5 if x is equal to 2, and f of x is equal to 1/2 x plus 2 if x is greater than 2. Now, if we had a graph of this, we could easily answer the question about where are the discontinuities. But it's, as we've seen, it's a lot of trouble to graph. And so let me suggest that we look at things here. That, to me, the only suspect place for a discontinuity is when x is 2, because that's kind of where all the graphs come together, isn't it? See, if we imagine this function for the x's that are less than 2, then the definition of the function is just y equal 2x minus 1. And y equal 2x minus 1 is a line, and as long as we're at less than 2, then it's just a normal line. And there's nothing strange about a line. On the other hand, if x is bigger than 2, then our function is just y equal 1/2 x plus 2, which is also a line. So on the other side of 2, we just have a line. Nothing suspect about that. That should act normally. The question is, what happens at 2? Is the graph broken at 2? And so that's really what we need to discuss. That's the only question, the only questionable x value, that is the only possible discontinuity is at x equal 2. That's the only place we might have a problem. So let's ask the question then. Is f of x continuous at 2? That's the question we want to ask. And remember, there are 3 conditions. And the first condition, then, we have to ask the question, is f of 2 defined? See, it has to be defined for it to be continuous at 2. Well, when we look at the function and look at the value x being 2, well, when x is 2, the functional value is 5. And so we can answer here yes, because we know that f of 2 is actually equal to 5 based on the definition of the function. So it passes the first test. The second test is, does the limit of f of x as x approach 2 exist? That's the second test. Now this is a lot more difficult. Okay, this is a whole lot more difficult. But let me remind you, in our limit discussion, when we talked about left-handed and right-handed limits, we said that for the limit of a function, for the limit of f of x as x approaches x approaches 2 to exist, it must be true that the sided limits exist. That is, it must be true that for that to be the case, that the limit of f of x as x approaches 2 from the left-hand side has to be the same as the limit of f of x as x approaches 2 from the right-hand side. That's the only way the limit of f of x can exist as x approaches 2. So let's consider those. First, what about the limit of f of x as x approaches 2 from the left-hand side? Now here's the crux of this argument. If x is approaching 2, let's maybe note over here. If x is approaching 2 from the left-hand side, that means that x is less than 2. If it's on the left side of 2, then it's less than 2. And if it's less than 2, then f of x is actually 2x minus 1, isn't it? So the limit of f of x as x approaches 2 from the left-hand side is asking the same question of what's the limit of 2x minus 1 as x approaches 2 from the left-hand side. Well, as x gets close to 2, we can simply do a substitution here. As x gets close to 2, it doesn't matter from the left-hand side. This expression, okay, if we're smaller than 2 but we're close to 2, then this is almost 2 times 2 minus 1, which calculates to be 3. So the left-handed limit is 3. Now, on the other hand, if we consider the limit of f of x as x approaches 2 from the right-hand side, well, if x approaches 2 from the right-hand side, that means that the x's are bigger than 2. It's coming from the right of 2, and if it's on the right side of 2, then it's bigger than 2. Well, if x is bigger than 2, then f of x is 1/2 x plus 2. So our limit really is the limit, in this case, of 1/2 x plus 2 as x approaches 2 from the right side. And of course, once again, if x is getting close to 2, then what this is getting close to is 1/2 times 2 plus 2. And we see that that calculates to be 3. So we see that the left-handed limit and the right-handed limit are both 3. So that tells us that the limit, our conclusion here then, is we conclude that the limit of f of x as x approaches 2 is the same as those two the left-handed and right-handed limit. So more importantly, it exists. Okay, the limit exists. So way back up here, we can say yes. Not only yes, the limit of f of x as x approaches 2 is equal to 3. So far, it's passed the first two conditions. Now, the third condition is this question. Is it true? That is it true or false? Is it true, my bad, that the limit of f of x as x approaches 2 is equal to f of 2. That's the third condition that has to be true, right? Well, here's what we know. The limit of f of x as x approaches 2 is equal to 3. But f of 2, we saw above, is equal to 5. And so this is not true, is it? The answer here is no. And if this answer is no, it fails that third condition. So we only had to fail one condition, but it was the last condition it failed. So here's what we can say. F is discontinuous only at x equal 2. That in the very beginning, we said that was the only suspect x value, and we found out that that x value is discontinuous at that x value. Now, on the next page, what I'd like to do is draw a graph of this function, just so that we can put these pieces together once again. Okay, so let me pause while I draw a graph. Okay, you can see on this page that I've created a graph of the function, the piecewise defined function. Let me just kind of give you a quick idea of what I did. I first considered x values that were less than 2. And of course, when I've got x values less than 2, then my function looks like y is equal to 2x minus 1, which is a line, but it's only a line up to where x is equal to 2. So I plotted some points, and you see I got this point, and I knew that line went along, but for only x is less than 2. So that value didn't come into play. And then I looked at the value x, whoops, I'm sorry, this function is up here at x equal to, I'm sorry, I miswrote that. Then I looked at the value x equal to, and in that case, from the definition of the function, y is 5. So the point 2 comma 5, which is the point way up there all by itself, is on the graph. And then I considered the x values that are greater than 2. And when I'm considering x values greater than 2, then what I have is y is equal to 1/2 x plus 2, which is also a line, but it's only a line for x values greater than 2. So I plotted a few points, and you see that the line I got. Now, we can see once we have this graph that the only suspect place, of course, is at x equal 2. And so we can see by looking at the graph that we have a discontinuity there. And it's, we can also look at the graph and note from the graph, three things. That f of 2 exists. It's equal to 5. Note that the limit of f of x as x approaches 2, well, as x approaches 2, we're coming this way, or we're coming this way to 2 on the x-axis, which means we're moving along the graph like this, or we're moving along the graph like this. But regardless, we're closing into that blank point, but that y value is 3. And so that's where the idea is the limit of f of x as x approaches 2 is equal to 3. See, as we come in from the left, y is getting close to 3, or if we come in from the right, y is getting close to 3. And that's the idea that the left-handed limit and the right-handed limit have to be the same. We have to be going to the same position on the graph regardless of the side we're on. But of course, the third problem, the third situation, okay, the limit exists and is equal to 3. That's really what I should have said, is the limit exists. But we can see here that the limit of f of x as x approaches 2 is not equal to f of 2, because f of 2 is way up there. And so we get a different value, and that's what we were trying to prevent earlier. So from the graph, we can see a little different take on it, but we didn't need the graph to actually make the decision that we're discontinuous only at x equal 2 only. This becomes very obvious. By the way, before we leave this particular type of function, let's consider a little bit different function. Consider f of x equal, let's do this, 2x minus 1 if x is less than 2, and let's say it's 1/2 x plus 2 if x is greater than or equal to 2. So we still have it defined at 2, and so it's defined everywhere. And just to make a point of what this graph would look like, I think we can probably tell pretty quickly from the situation that we have here. Let's say this is where 1 is, and this is where 2 is. So we'd have 1, 2, 3 right here. Okay. See if I can draw this. So when we start drawing this left-hand side, that's where x is less than 2. But then when we start drawing the right-hand side, when x is greater than 2, greater than or equal to 2, and then we're graphing y is equal to 1/2 x plus 2, then when we put a 2 in for x, see, that's allowed, then we actually get 1/2 of 2 plus 2, which ends up being 3. So the point x is 2 and y is 3 is on the graph. Well, x is 2 and y is 3 is this point when we start graphing the other part. And when we graph the rest of the points there, we'll get a line that comes out like this. So over here is the part of y is equal to 1/2 x plus 2 for x is greater than or equal to 2, and down here is y is equal to 2x minus 1 for x values that are strictly less than 2. But those two graphs actually meet, don't they? So in this case, we would say f is continuous everywhere. And the point is that the only suspect place, when we look up here, we suspect 2 is a problem. 2 might be a problem for continuity. Because that is a place that the graph might be broken. But when we actually look at the graph, it's not broken there. And so, like I said before, the function f is continuous. There are no broken places and there are no holes. Okay, and our last problem for this section on continuity, you can see as it reads, find the value of k that makes the function g of x equal x cubed plus k if x is less than or equal to 3, and it's kx minus 5 if x is greater than 3. So find the value of k that makes that function continuous. And when we say just continuous, we mean everywhere, that there are no discontinuities. Now, remember, there's going to be some number, like a 5 or a 2 or a 1/2, where it will read x cubed plus 5 or 5x minus 5, or x cubed plus 1/2 or 1/2 x minus 5. So we're looking for that special number that makes this function continuous everywhere. Now, I might point out that as we've seen before, the only suspect position, the only suspect x value is x equal 3. I mean, and after all, just consider y equal x cubed plus k. No matter what k is, that's just a continuous function, that there's nothing strange going on there. X cubed plus a number will just be the x cubed function shifted up or down. So as long as x is less than 3, then that function is continuous. So this part, it will be continuous no matter what k value we choose. That's not a question. Likewise, if x is greater than 3, we're looking at something that's just y equal kx minus 5. And in that case, of course, whatever k we make the decision on, that's just going to be a line. And so as long as we're greater than 3, that's going to be continuous. So it doesn't matter what we choose. Whoops, that's going to be continuous. It doesn't matter what we choose for k, then that will be continuous. So we've got to find the k, though, that makes these two pieces match. See, the only place that we might have a problem is it might be broken at 3, so that the top part gives a different value than the bottom part would be. So, you know, in terms of calculus, what we really need is the limit of f of x as x approaches 3 from the left-hand side to be the same as the limit of f of x as x approaches 3 from the right-hand side. I mean, after all, the first condition about continuity at 3 is that f of 3 exists. See, that condition is true because we have a way to calculate f of 3. It will be x cubed plus k when we know what k is. So the second condition, we have to have the limit of f of x as x approaches 3 to exist. So that's the next condition that we need. And for that condition to be true, the left-hand and right-hand side limits have to be the same. Now, like I said, it goes a little further than that. We can just imagine that we need these two ends to meet together. Okay, that's really what we need. But, and you'll see that that's what's going to happen here. As f of x, as x approaches 3 from the left-hand side, then actually what we end up having over on this side is x cubed plus k. Okay, as x approaches 3 from the left-hand side, then that's the value, excuse me, I'm sorry that I really goofed this all up. This is a g of x, isn't it? And this is a g of x. Our function's named g. I'm sorry about that. So when we're on the left-hand side of 3, we're less than 3, so we're using the first equation. And when we're approaching 3 from the right-hand side, that means we're bigger than 3, and so we're actually using the second equation. And so our two limits end up looking this way. Well, these are easy to calculate. As x gets close to 3 from the left or the right, we would calculate this left-handed limit as just simply being 3 cubed plus k. And of course, on the right-handed side, we would end up with, remember we're replacing x with a 3, so this becomes k times 3 minus 5. And that's equivalent to just seeing what the value of y would be, whether we use the top equation or the bottom equation to calculate the value of y when x is 3. We want those two to have the same value. So over here we get 27 plus k, and of course over here we have 3k minus 5. And so we ought to be able to solve the equation that makes those two equal to each other. And we'll do that by adding 5 to both sides and subtracting k from both sides. So on the left we have 32, and on the right we have 2k, and so when we solve for k, we get k is equal to 16. That's the k that we need for this function to be continuous at 3, and that's the only question we had in mind. Okay, we decided it would be continuous at all other places. So that's the answer. Well, that concludes our discussion about continuity. I hope this has been helpful.